Okay, can you hear me? Hi, I'm a graduate student in Tom's group, and I spend most of my time collecting electron diffraction patterns of aquaporin crystals. And aquaporin crystals are quite nice, as you've heard time and time again during this lecture. And so they're really nice to learn how to collect diffraction patterns on, and because they diffract very well. Unlike most crystals, where you spend years and years trying to get decent crystals that you can actually collect, once you get to that point, it's time to leave or someone else will take over. But for me, I had nice crystals to work with. So I'm going to explain how we do it in our lab. Every microscope is a little bit different, JL versus FEI. One advantage of our microscope using a Polara is that you can very easily change from diffraction to imaging back and forth. This can be used for tomography. So it's a pretty widely used microscope. And at the end, I'll describe one example of where that was really useful for one of the projects I've worked on. So the outline of my talk is pretty simple. Actually, when I was a student in this course 4 years ago, Janet gave the lecture on diffraction data collection, so I modeled it somewhat after hers with a short description of how you actually form a diffraction pattern, a comparison between imaging and diffraction, and then actually how you collect diffraction patterns. So it's a very similar picture to what Janet shows, so how you make an image. To make a diffraction pattern, you just change the position of the lenses. And so your projector lenses, rather than magnifying the image, you magnify the diffraction pattern. And that's what they mean by camera length, is how much magnification you get by the projector lenses. I'm not going to go into any more detail. If you have more questions on how you make a diffraction pattern, I can answer those. But that's not really my expertise, so I don't want to explain that wrongly and have to have someone who really is an expert, which there are many people here correct me. So what is the difference between imaging and diffraction? So as you've seen, this is an image, a negatively stained image of a 2D crystal. I use a negative stain image so you can actually see the lattice in it. But a diffraction pattern, you can see, is quite different. There's no image itself. It's just reflections. So what the main difference between that is it's much easier to get the information, but what you see is what you get. You can't unbend it, unlike a crystal where if you have a slight lattice defect here and here, you can make it better. If you take a diffraction pattern, whatever your diffraction pattern is, that's the quality of your data. And now just in a little more detail. So imaging is a real space way to sample your crystals, whereas diffraction is reciprocal space. So you're directly sampling the Fourier terms. Unfortunately, what that means is you lose the phase information. You directly sample the intensities, which can be quickly converted into amplitudes, whereas with images, you sample, because it's a real space image and you're converting it to Fourier terms, you can sample both the phases and the amplitudes. Some other major differences is that for images, you can collect images of any crystal. It doesn't matter how big, how small, how well ordered, how poorly ordered, if it's mosaic. If you have an image, or if you have a 2D crystal, you can take an image of it. With a diffraction pattern, it doesn't really work out like that. You need crystals that are fairly large and fairly well ordered. Otherwise, the inelastic scattering, which is this region here, will mask out everything and you won't actually get any information. Another difference that I've already described is that you have good phases at all resolution ranges from images, whereas diffraction, you have no phases at all. One of the major advantages of diffractions, on the other hand, is that you get accurate amplitudes at high resolution, whereas with images, because of the modulation of the CTF and the dampening of the amplitudes, you end up with fairly poor amplitudes at high resolution, particularly ones that are close to the CTF transitions. It's fairly hard to correct for that accurately. And so by using diffraction, you can sample those amplitudes very well because there is no CTF and there's not the modulation of the amplitudes, like I said here. And the last thing is that there's no unbending. So whatever the resolution that you see in your diffraction pattern, that's what you get. Whereas with 2DX and MRC, you can actually start to improve the resolution by unbending your crystal. So one of the reasons, so if we can get both amplitudes and phases from images, what's the point of collecting diffractions? Like I said before, amplitudes from images are fairly poor at high resolution. If you collect a lot of images, you can start to make up for that. But for the most part, it's a lot easier just to collect diffraction patterns. The resolution of diffraction is usually just limited by the quality of your crystals. So if you have really great crystals, you can get really great resolution. You don't have to worry about all of the CS and all these other defects in the microscope that can start to degrade your image quality, the MTF, all those things that people have talked about. With diffraction, it's pretty much if you have a spot, it's there. You don't have to worry about losing it somewhere in the microscope. And one really nice thing that you can do with diffraction is that if you have a special case where you have a previous set of phases, you don't need to collect images at all. You can just merely collect diffraction, which are much easier to collect and solve your structure using indirect methods such as molecular replacement, which rather than spending years to collect data, you can do it in maybe a year or two and have your whole data set, which you can then calculate the structure with. So this is just a quick image. These are both 2D crystals of aquaporin 0, and so this is an image, and you can see that the IQ spots kind of fall off around 4 angstrom, maybe a little better, whereas the IQ spots of the diffraction, or the spots in diffraction, you can see extend beyond 2 angstroms. So these aren't from the exact same button, but they're similar quality crystals. With diffraction, you can just tend to get higher resolution. Normally, this isn't an issue because you're limited by the quality of the crystals. Most crystals, as Werner said last night, don't extend this far, so you're not worried about the loss of resolution. You're probably going to get the same quality from both imaging and diffraction, but this is just a lot easier to do. So when can you actually collect diffractions? The basic rule of thumb is that if you have crystals that diffract to better than 5 angstroms, then you can probably collect a diffraction pattern. The other thing you need is you need a larger crystal. You can't collect on anything that's much smaller than 1 by 1 micron. If you have the ability, a 2 by 2 micron or even a little bigger is nicer because you get a higher signal to noise. It's also easier when you tilt because as you tilt, the surface area of your crystal gets much smaller in the plane of the beam. You also need to make sure that your crystals have long-range order. If they have a patch of very good crystal here and a patch of very good crystal there, everything in between will just contribute noise, and most likely they won't have the same register, and so you'll end up blurring the spots. It'll be as if you average the 2 sets of crystals together. And you also need to have, within a sample, pretty homogeneous samples. You only want maybe 1 or 2 different populations. If you have too many different populations, diffractions in a few examples have been very difficult to segregate by themselves, particularly if the unit cells are very similar. It's almost impossible to take diffraction patterns of 2 crystals from the same sample and distinguish them on their own. So how do you set up the microscope for diffraction? Most people here know how to set it up for imaging. It's the most common way. But for diffraction, we do it a little bit differently. Everything to start is the same. You align the microscope, pivot point, gun shift, beam shift, everything that Janet was talking about and what Hans will talk about later. The most important things, again, are the beam coherence and that you have a parallel beam. For diffraction, we have a little bit more range into how good the beam can be. We don't need to use as good of a microscope. In our lab, we've been able to record diffraction patterns at better than 3 angstrom using a side entry stage on an F20. The better microscopes are obviously easier, and you're going to get a higher yield of better data, but diffraction tends to be a little less restrictive as to the quality of the microscope you need. So next thing is that rather than you don't need a bright beam at all. To increase the quality of the beam coherence, you use a very small spot size, usually the smallest one that your microscope can attain, and you also use a very small condenser aperture. What this results in is an extremely weak beam. Usually you can't see it. It's just your screen looks as if it were black in imaging mode. But the nice thing is diffraction patterns are insensitive to translations. So you can take a very long exposure. You can take a 30-second or even a minute exposure of a crystal, and you don't have to worry about drift or any of the specimen-induced beam movements, or beam-induced specimen movements, sorry. Any of those things that happen that would destroy an image for diffraction patterns, you're still okay. And the other thing for the setup is that you want to use a CCD camera. CCDs are nice because they have extremely high dynamic range. Most of the time, your diffraction patterns are going to be several orders of magnitude different between the weak spots at high resolution and the low spots and the strong spots at low resolution. And also, you have to worry about the very high inelastic scattering near the origin. So this is how we set it up on our Polara. We used a magnification of about 40,000 in imaging mode We center the condenser aperture. We focus the lens, again, using the wobbler and the eccentric height. We then overfocus the condenser to spread the beam about twice the size of the average crystal. That way, even your largest crystals will be imaged entirely, and your smallest ones, you won't burn ones that are adjacent. That way, if you have a lot of crystals close together, you can get a pretty good image of all of them. Then you switch to diffraction mode with the appropriate camera length. The camera length is dependent upon the resolution. You want to try to get the most spots and also have the largest spacing between them so that you can accurately determine the background between the spots. Then you insert and center the selected area aperture. We use a selected area aperture because this can mask out everything that's not your crystal, and this will improve the signal to noise because you can't, like an image of a crystal, you can actually mask it out computationally. With a diffraction pattern, you don't have that option, so you mask it out with an aperture. The next thing is you focus the diffraction pattern to a single spot, and then you insert the beam stop. Because if you don't insert the beam stop, you'll burn your CCD in 1 or 2 images. The direct beam is extremely intense. And then you use low dose. Once you've aligned your microscope for diffraction, you then can align search mode. So again, this is what crystals look like in defocused diffraction. You can see they're pretty blurry, but you can find them quite easily. You mask them with your selected area aperture. We set up the search mode exactly as Janet described. Focus mode is set up to be identically to exposure mode, but you don't ever use it during data collection. You just switch from search to exposure and back and forth. You skip focus because you don't need to focus on every crystal. So how to actually collect one diffraction, you identify one of your crystals in search mode. You just move your beam so that you have your selected area aperture just around this one crystal. You then mask it with the selected area aperture, blank the beam, switch to focus mode. While the beam is blanked, switch to exposure mode. So like I said, you just skip focus mode entirely, just going from beam search to exposure, but you don't want to skip them, otherwise you'll introduce hysteresis into your microscope. You then lower the phosphor screen, quickly unblank and blank the beam to make sure that the beam is blocked by the beam stop. Sometimes as you're moving around, it'll shift a little bit, and if you take a picture with it shifted, you can burn a permanent hole in your CCD that is a way to really upset your boss. Then you insert the CCD, raise the phosphor screen, and then you record the diffraction pattern for 10 to 60 seconds, depending on the crystals and the beam intensity and a few other things. And then you return to search mode and find another crystal. And you do this over and over again. The greatest advantage is that you immediately have your diffraction pattern. So you can see, as soon as you finished taking the diffraction pattern, you have your image. You know if it was good or not, which lets you quickly determine, is this a good grid, is this a bad grid? So you can quickly switch out a bad grid without having to spend 2 or 3 hours looking at it. And you also know, is this a better area? Is this flat enough? Should we move to another grid square? Yes? I keep everything aligned and I blank it, and then I unblank it quickly and then blank it again so that I can, with the lights off, you can see the outline of the diffraction spot around the beam stop. What I'm asking is, which do you move? Do you move the beam stop, or if it's off, I'll go back and I'll switch back to search mode, move to another area, realign everything. I try to keep the beam stop centered in the center of the CCD array at all times. So what I'll do is, when I'm starting data collection with a CCD camera, I'll put in the beam stop and I'll take a picture, and I'll go, since we have a 4K by 4K, I'll look for 2048 and 2048, make sure that's the center of my beam stop. If it's not, I'll move it around until it is. So I keep the beam stop fixed, and I'll move the beam until it fits the beam stop. That way you don't lose. So if your beam stop is here, you're not going to have the same resolution in both directions. Are there any other questions? I'd be happy to answer them during. Yes? You move the beam with beam fills, right? No, you move the beam with diffraction shift. diffraction beam shifts, the dials. It's below the. Any other questions? Okay, I'll continue. So, yes.
If in diffraction mode the central spot is focused and on the same time your objective aperture is focused, then you have chroma-free alignment. No.
As you can.
Actually, it depends on what you are doing. That's what I learned from him as well. If you are using what's called the nanocosmos, that's how you can do it. Because in that case, you get the parallel beam. You need it to be focused at where the lens is, and that's very close to the objective aperture. So if you are using what's called the nanocosmos, where you allow the beam to be parallel, there's a point where you get parallel beam. Remember how Janet was describing? To get a parallel beam at your central, the spot you're starting, your source needs to be at the point of your back focal point, right? Back focal point. So, in another way that you look at the other way around, you can find a point in your lens system if it's at the back focal point and focus, then the other side of it is going to be parallel. So the objective aperture happens to be really close to it. So if you go to diffraction mode, and you'll be able to focus the beam to one spot while you get a good focus on the objective aperture, you end up with a parallel beam in that condition. If you have a dual microscope that doesn't have a nanoscope mode, then it's actually there is something similar.
One thing I forgot to mention is that for diffraction, you remove the objective aperture. Otherwise, you'll start to see shadows at the very edges where you're truncating spots. So we just remove the objective aperture entirely. Okay. So how do you pick the camera length? You want to have a camera length that's not going to cut off the high resolution spots. As you can see here, this line would probably continue beyond the edge of the CCD. And so this camera length is too long. You're going to lose the spots. But on the other hand, you don't want it to be too short, because after you collect the diffraction pattern, you then need to subtract the background so that you can the intensity of each spot. So if you have these spots too close together, it gets very difficult. For untilted images, it's not quite as much of an issue. For tilted diffraction patterns, or diffraction patterns of tilted crystals, you actually start to get these spots to blur most of the time. At higher and higher tilts, it gets more and more severe depending on how flat your specimen is. And if you have a severe blurring, you can almost get these spots to run together. So you want to make sure that you have a nice spacing between them so you can still subtract the background, even if your spots start to elongate. And the other thing is the diffraction exposure time. Because every crystal can withstand a slightly different amount of radiation, and your exposure isn't going to be identical every time, what you can do is take a series of exposures of the exact same crystal for a short time, 5 or 10 seconds, and then look at the loss of the high resolution spots. So you can see here, after 10 seconds, you can see these spots here, but after 30 seconds, they're completely gone. So what I would do then is say 10 plus 10 plus 10 is 30, so I would take a 30-second exposure. I didn't show exposures 2 and 3, but those you could very faintly see this. You can see maybe it's almost there, but at this point it's too burned to be useful. So I would take a 30-second exposure for this rather than, and that's how we recalibrate the amount of time we take it, because the beam is so weak. If you just try to measure the beam by the screen, it's 0 or 99.9, whatever your microscope will tell you. It's so low that it can't detect it. And now I'm going to show just a series of examples of what happens when you do something wrong in either your alignment, your specimen preparation. Just to make it easy, if someone ever tries to collect diffraction patterns and they don't look right, some examples of things that and how you can correct it. So this is just poor specimen embedding. You can see how all of the spots are very smeared and start to run along the lines, so they're starting to broaden in both directions. This is just because it was too dehydrated when I prepared the specimen. Did you have a question? And then the ring around the outside is usually caused by ice. This is at about 4 or 3 angstrom resolution. If you allow contamination to build up, you start to get this diffuse ring around the edge of your diffraction patterns, and this will cause your high resolution spots to be lost within there, and they're not recoverable. So this is something you also want to try to avoid. If you have an astigmatism in the diffraction, then you'll end up with a blurring of the spots in just one direction. Usually you can't see it as it's very slight. I extended these quite severely so that it would be visible in the diffraction pattern, but you can see how it's not, this is an untilted image, but it looks like a tilted image. In a tilted image, you'd usually have very clean spots here and very smeary spots at the edge, but these ones are smeary all the way through. So this is an issue with the diffraction astigmatism. If you have a poorly focused objective lens, you'll get another type of error where you'll get sharp, strong spots on one side, but on the other side, the spots are very weak and somewhat diffuse. This is caused when you have your objective lens off by 100 microns or something. And normally this wouldn't happen, but if you're looking at your diffraction patterns and you're taking them, and you can't quite figure out why it's going to look so weird, one of the reasons may be that your objective lens is way off. Non-tilted.
So why would that be asymmetric on one side versus the other?
I don't know. But this is something I've had. For whatever reason, one day I forgot to set the eccentric focus, and I spent about 3 hours collecting diffraction patterns, and they all looked terrible like this. And at the end, I had our EM manager help me, and he quickly set the eccentric focus, and this was gone. So unless there was something else that I didn't know, I'm pretty sure this is caused. Though this might be a 20-degree tilted pattern. I'm not certain, but it looks untilted.
So when you say steady, you mean that between your sample and eccentric focus?
That's how I set the objective lens. That's how I focus the objective lens. Right. So this is off by 100 microns or so. And then one thing that's also very common is if you have crystalline sugar, you end up with these blurry squares in a hexagon, and it's pretty clear when you have sugar spots. This is usually when your specimen is a little too thick. And this is a 20-degree pattern, but you can already see that the spots are blurred. This would be the tilt axis about here. And you can see the spots here and here are blurred, because if you have a thick sugar embedding, you're going to end up with your crystals not being very flatly adhered to the carbon. You're going to end up with waves, and this will cause your spots to smear. So now going into the collection of diffraction of tilted crystals. This is the most important, but also the most difficult part of diffraction data collection. One of the nice things with diffraction is you do have the ability to collect 60 and 70-degree patterns if you have a good crystal, but they're still quite difficult. Some tips that I've found that work best for me is to really make sure I have the best possible. I didn't know my phone worked in this country. That's strange. So, sorry about that. I try to prepare the best possible specimen prior to moving to tilted. So I really work at getting a very good specimen on a regular basis with the untilted diffraction patterns. Another thing is you need very good spark-free carbon. This can take a while, but it's worth the effort to invest to really get very nice carbon. Yobu gave a demonstration on how to do this earlier, and you should really test it by the light, because if you have bad carbon, you're never going to get good diffraction no matter how much time you put into it. So it's really worth it to make nice carbon at the beginning. You'll get much better data out in the end. And then the last thing is to make sure you don't have any contamination. If your microscope contaminates your crystals quickly, try to get the sample in and collect data as quickly as possible. And then when you start to see the contamination rings, switch the specimen and try the next one. But it's not worth collecting data on a contaminated specimen. And then one thing I've also found is that within a particular grid, you can get a large variation in the quality of the diffractions. So I try to sample as much of the grid as possible before I start collecting data in earnest. Try to find the best areas, particularly since we use the carbon sandwich. There can be a pretty strong gradient in the thickness of the sugar from one end of the sandwich piece to the other end, and so I really try to find the best area and then collect as much as I can from that area. Why do we use it? Yeah. It gives much better data. The quality of the resolution, the sharpness of the spots are all, in my hands at least. It may be different in someone else's hands, but for me, it's always 30 to 50% better with the sandwich. It could be that one of the biggest issues is that I don't have dehydration issues. With the carbon sandwich, because it's a double layer crystal that we work with, it needs to be a fairly thick sugar layer. And from one of my problems, particularly with trehalose, is I always would blot too much and the crystals would be dehydrated, whereas with the sandwich I can get a very nice even layer, not throughout the entire grid, but within a particular region of good, well-embedded crystals that'll diffract quite well. What is the concentration? I use 4% in the 4% to pick up, and then either water or 0.5% with the loop, depending on how humid or dry it is that day. And I've tested everywhere from 1 to 10%, and 4% consistently gives the best embedded specimen. Did you have a question, Tom? Yeah, and this was another thing that was discussed earlier. And some crystals just seem to be happier in the sandwich, and some don't prefer it quite as much. And for me, it is much better in my hands. And that's also the case. We've had a few other people work with aquaporin 0 2D crystals, and consistently we get better data with the carbon sandwich. And at the bottom that you can't see, I always reset the objective focus with each grid square and set the eccentric height every time as I switch from grid square to grid square. And then what happens when your specimens aren't flat? You can see this is a nice isotropic diffraction pattern. This is a 60 or 65 degree pattern. Whereas this one, you can see that the spots are fairly sharp along the tilt axis, but are almost non-existent perpendicular. And this can be caused by many issues. If your sugar is too thick, if you have a slight tear in your carbon, if you have a slight fold or bend. And so these are things that I always try to look out for. As I said, I look around the grid and try to find the best area. If I see one of these slight tears, I know that this is a grid square I should avoid and move on to the next one. Same with these folds. Even if you're quite a ways away from the fold over here, it's not going to be flat enough to collect good data with. So it's better just to move on to the next grid square where you have a nice flat, even carbon. And what I just talked about at the very beginning is that if you have a heterogeneous sample with diffraction, it's very difficult. Even though you have hundreds, in some cases thousands of spots, it's very difficult to segregate the different diffraction patterns just on their own, because there's no reference. You don't have an image to look at to say these two images are the same. You can try to put two diffraction patterns together, but they're never going to have the same tilt and tilt angle. So this is what happened with my most recent project, is I tried to merge diffraction patterns, and I ended up with this very large smear in the low resolution range, and the high resolution range you can see isn't too much better. And so after looking at it for a while, I realized that I'd had multiple crystal forms in one button. This is all from one 50 microliter button I collected all these diffraction patterns from, which usually you'd assume would be one crystal. But looking through the literature, there are a few examples where even within one sample, there were two or more different crystal forms that were present. And so here's just the diffraction patterns, and if you can see the difference, it's impressive, but I could never see them. These are all untilted crystals, and I could never find any difference between them. But when I then collected projection maps of these, just taking images on a CCD and quickly using 2DX to calculate the projection maps, you can see they're quite different. So this is a P121, P4212, P4, P1, P422, all within 1 day of collecting data. I took images, and these were all just vastly different ways that because it's a two-layer crystal, these are just different ways that the two different crystal layers can come together. And since even the untilted diffractions you couldn't segregate, if you have unit cells that are quite different, you can use untilted diffraction patterns to discriminate. But because these were almost identical regardless of which crystal form, I couldn't segregate just on the basis of the untilted diffractions. So what I had to do was use a method that Fujiyoshi's lab first used with aquaporin 4, was collect a diffraction pattern in an image. And this is where having a microscope such as the Polara, which can rapidly switch from imaging to diffraction and back and forth in about 5 or 10 minutes, is quite useful, as I could go through, take a grid square, collect the 15 or 20 diffraction patterns, quickly switch to imaging, collect images of those same regions, and then go on to the next grid square. Whereas with a microscope, it's more difficult to switch back and forth between modes. It would have taken much more time. And so this is what the merging lattice lines look like at the end. We're going to have a session on diffraction merging, I think Thursday, where you'll be shown how to actually make these lattice lines. But you can see how much better they are, that there's actually a modulation of the intensity with respect to resolution, whereas before it was just a smear. And then this allowed me to build this atomic model using molecular replacement, which I'm going to discuss more on Thursday. So how to take diffraction patterns and actually convert that into an atomic structure. And then some references for how to collect diffraction patterns. This is an old one that's quite good. Bob Glazer's book has a great chapter on collecting diffraction. And then Tom and I and a few other people in our group are writing a methods in enzymology paper on how to collect images and diffraction patterns, which has some good protocols and has more in-depth details for some of the protocols I described today. Thank you.
Question?
Actually, I have a question. You always need a known structure of your protein in order to do molecular.
Or something closely homologous. It needs to be about 30%.
And if you think that you have a complex of proteins, with one known protein structure and the other one is not known, is it possible to draw the other one?
It depends on how close they are and also how much of the total mass of the asymmetric unit cell it is. Usually the rule is about 30% identity and about 20 to 30% of the volume is made, or of the mass is made up by that component. It varies.
So let's say if it's 50%.
No, better than 20. So if it's 50-50 and you know one of the 50s, odds are you should be able to use molecular replacement. It may not always work. With electron diffraction data, it's always harder because we have higher R merge, higher R Friedel, so the data is not quite as nice as what you're going to get from an X-ray diffraction data collection, but odds are it should work.
Yeah, I didn't quite understand what you were doing with the so you take first a diffraction pattern and then an image to check what kind of crystal form you have.
Yeah, so I would take a diffraction pattern of one crystal, and then save the location in the compu stage, and then of the whole grid square, switch to imaging mode, and then either keep it tilted, or later I found it was easier just to switch it to 0 degrees, and then take an image of all of those same crystals, and then I could quickly quickly calculate an FFT, and then use 2DX to get the projection map, and I could easily see which of the various crystal forms I had.
So if the difference in crystals is just a shift of one layer relative to the other, you wouldn't see a difference in the diffraction pattern because it's just inflated.
Yeah.
So you have no other way to find it out.
And that was what we discovered, is that because the unit cell is identical in both. With diffraction, I tried for a few weeks and I could never get anything. And looking in the literature, Fujiyoshi's lab had done this by switching from diffraction to imaging, and that worked pretty well for us.
collect amplitudes from diffraction and your traces from images are of lower resolution, you have to either borrow traces from X-ray crystallography or do a phase extension or something like that. And I'm very interested on knowing how you guys do the phase extension with aquaporin, and also how easy is to extrapolate that method to other membrane structures.
We don't need to use phase extension because there is an atomic resolution structure of another aquaporin that we initially used, and then I've just used Tamir's structure of the original aquaporin 0. But for phase extension, you tend not to want to use something like aquaporin 0, which has an extremely high symmetry and has only one unit in the asymmetric unit cell. You'd want something that has a non-crystallographic symmetry so that you could start to take advantage of density modification a little bit more. So some of these crystals that have the lower symmetry, like this P121, has a fourfold non-crystallographic symmetry. And that one may be possible to use phase extension to extend from, say, 5 or 7 angstrom from images to atomic resolution. But because we already have the phases for molecular replacement, I don't collect images at all. This was the first images that I had to collect were to try to segregate these different crystal forms.
Did you take those diffraction patterns at helium temperature?
No, these were all at liquid nitrogen temperature. And our Polara is set up for using both, and in my hands there's no noticeable difference. I think the quality crystal to crystal is greater than the quality difference from helium to nitrogen, so I could never tell a difference. No, 3D nanocrystals, because unless you have just a very defined thickness, then it's impossible, because you don't know how many unit cells you have in Z. If you have 2, 3, 5, 7, your diffractions are going to be different.
So your method, they have to combine with the image mode. So combine both of these image and diffraction.
Yes, so the general way to solve a structure is to collect phases from images and then amplitudes from diffraction patterns. In the case of aquaporin 0, which we've actually done a comparison, there's very, very little. In other proteins, there have been, I think EMRE is probably the most famous one, where there was a significant difference between the X-ray structure and the EM structure. Even though the EM structure was lower resolution, you could see the helices, and you could see that there was something different between the two. But aquaporins are, as one of the reasons why they make such good 2D crystals, is they're very stable, very compact proteins. There's not a whole lot of movement. It's not a transporter where you have a large domain shift. These are very stable proteins, so it wouldn't be likely that you would have a large change between the structure in a membrane and the structure in a... I can sample to about almost 75 degrees. So I sample somewhere around 93 or 94% of Fourier space. So the missing cone with my crystals, because I can tilt to such high angles, is extremely small. And also when you use crystallographic refinement, you force bond lengths upon the structure, and so the differences are extremely small. The RMSD is about 0.4 between an X-ray structure and an EM structure. So they're superimposable. If I gave you the two, just the backbones, you wouldn't be able to tell the difference.
At which resolution you can propose a localization and a number of lipids?
It depends. So it depends on how well ordered a particular region of the map is. In this newer map that I have, there's more lipids that are visible in one leaflet than the other, but in a particular region, there's more on the top leaflet than the bottom leaflet. So it depends on the map. It's just like any structure. You're going to have some regions that are going to be more well ordered than others.
Typically, in my session, how many
It's entirely variable. I can go for a week without getting any, and then in a single day I've gotten, I think the most is close to 100. So if I get a good sample, it's great. If I don't get a good sample, it's just keep switching until I do.
Okay. There are no more questions.